Hi everyone and welcome to our first video for topic 21. In this video, we're going to be reviewing the area of parallelograms, including squares and rectangles. So to start off with, let's do a very brief review. What is area, right? What is area? If I was to draw a rectangle, say like this, let's go a little small. There you go. And let's shade that in a little bit, right? If I was to draw that rectangle, what is the area of that rectangle? Take a second, think about it, pause the video maybe, and come back after you have an answer. All right. Let's say you said the area, looks like maybe 20, right? Maybe, how did you get that? Let's talk about it. Well, maybe you went inside here and you counted the number of squares. You might remember area is the space that a two-dimensional shape fills up, right? The area it covers, right? Very good. We've been building up to this for the entire year, right? Area is very importantly the space that something covers, right? So to be able to find this area, I need to find how much space it covers. We measure space with different measurements in the real world, like inches or feet or meters or yards or whatever. These squares on the screen represent units. We don't know what unit it is, right? How we're measuring it. We could say it's inches or feet or whatever, but that's one of each unit, right? So I could say this side down here is 5 feet, okay? And this side over here is 4 feet, right? If I know the feet of the two sides, I can find how much space it covers because I know each of these is a square foot, right? Because they're squares. So I could count it 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 go to 20, right? But if I gave you a way bigger shape, say this one, right? That would be very inconvenient to count. So how can we do this a little faster than just straight up counting? Well, what you could see is I go 1, 2, 3, 4, 5, right? That's a row of 5, the width of it. And then I got 4 of those such rows, right? So I do it again, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Anytime in math, you keep repeating yourself over and over, right? That's a really good sign that you found a pattern that you can use to make things faster. If I'm doing the same thing every time, I don't want to keep repeating that by hand. I want to make a shortcut to do that for me. In the same way that we make tools in like kitchens or whatever to do something for me. If I know, hey, blending is always the same process, I might as well make a blender to do the job for me, right? In this case, what is the job that this is doing? Well, I got a row of 5 and then I do that 4 times. Notice that 4 is this measurement right here. I also could have seen this a little differently. What if I had instead seen it, instead of going this way, I was going this way? 4, and then do it again, and again, and again, and again, right? That time I'm repeating it once for each column, the 5. When you repeat addition, that is multiplication. So what you're seeing here is not counting one by one. That is actually 4 times 5, or you could also see that as 5 times 4. They're both going to equal the same result, which is 20 square units, right? Or in this case, 20 square feet. We also can call that, another word for it would be 20, or another notation would be 20 feet squared, or you can abbreviate it as 20 square feet. That is my answer for the area of a rectangle. Now, we don't want to be able to figure this out. We want something generic to figure this out. What if I don't give you the measurements, right? What if I say for any rectangle, how would you find the area of it? So let's examine some example rectangles of different shapes, right? So I could see a 3 by 3, that's a rectangle too. It's a square, but it's also a rectangle. I could see a 2 by 6. I could see a 4 by 5, like we just did, right? I could see, you know, this really big one, right? I don't even know what that is off the top of my head. How would I find the area for each of these different things, right? So for this one, I have 3 rows and 3 columns. So that's going to be 3 times, right? So it's 3 times 3 to get me 9. For this one, I've got 2 by 6. So I do 2 columns, 6 rows, right? And I get 12. We already did this one. That was 20. And then I don't even know what this one is, right? Now, what gets tricky is what if I say, okay, I changed my mind. I don't want to do 2 by 6 anymore. I want to add another row. So I want to go, you know, 3 columns, right? Or I want to add another row. So I want to go 7 rows. How would I change the equation to adapt for that, right? If I add another row here, what needs to change in the equation? Well, what I got to get rid of, right, is I've got 7 rows now. So that number changes. When you see one thing stay the same and one thing change, you have discovered a variable, right? So this spot right here represents not just 6, not just 7, it represents the number of rows. We're going to call that the height, okay? So that's h. You also might see it called length or width. I don't like using those for my generic equations because they get confusing based on context, right? So I'm just going to call it the height, okay? So that's going to be the height. And what is that being multiplied by? Well, notice when I added another column, right? That's when I needed to change this here. Now I've added another column, right? So that's going to change and that's going to become 3 by 7, right? So that represents what we call the base. And that's this bottom bit right here, right? The base of the shape, like a skyscraper's base. So I've got base times height equals area, right? That's the generic equation for a rectangle. Now for a square, you'll notice that if it's going to be a square, when I add another row, I also need to add another column, right? And then I need to fill that last spot in right there. When I do that, rows and columns change at the same time. So both of these are either going to be base, right? Because they got to be the same, or it's going to be the height times itself. So in other words, I just take one of those two things and I square it in order to find the area for a square, right? So whenever I change that, both of them change at the same time. Okay, so the generic equation that we have for rectangles and squares, right, is just base times height. Now notice again, this entire paper is graph paper, right? So you need to measure things with square units to get area. That means that almost all area equations are built upon squares at a certain point, right? So let's review a trickier shape here and see, can we figure out how it's based on squares, okay? So we're going to talk about the parallelogram. If I take a parallelogram, remember, that's any two parallel sides. Let's make it a little easier. Let's do 5 by 5, right? And if I connect these to make a parallelogram, notice it's tilted a little bit, right? Now, I could tilt it even more drastically like this and make it even farther away from being a square or a rectangle, right? So let's do it with this one, really drastic. How would I find the area of that? You're going to notice, right, that now when I fill this in, it doesn't look as convenient as it did before, right? This filled in area right here has some partial squares in it. You see that? Things that are not completely filled in. So I can't just count the number of squares now. I also don't have rows and columns to count in the same way. There are, some completely filled in squares here that I could count one by one very slowly. And I got all these like half squares that make things tricky, right? Now, yeah, you could still count the half squares and add up the half squares and so on and so forth, but there's got to be a better way, right? We don't want to count one by one because what if I made a way bigger version of this, right? I could have made this look like, this, right? Ooh, really big, really terrifyingly huge. I don't want that, right? So how can we make this generic? How can we figure out the way to always solve for this, right? So let's chat about that. Well, let's start by trying to figure out how can I make this look like a rectangle? Is there some way to reimagine this shape so that it is a rectangle? Because if I can figure out how to, break this up into pieces and make them into a rectangle, that might be more convenient, right? Well, if I was able to take this part off, okay, so I'm going to pretend I'm slicing this part off right here. You see that? If I took this part off, I could transplant it somewhere else, right? I could put it over, say, well, it seems to have a pretty similar slope. So I could try to put it over here, 4 over, 4 down. That would move very nicely to fill in that spot, right? So in other words, if I took this part away, subtracted that, right, and I added it over here, it would now create one big rectangle, right? So if I was to see, okay, now I've got a rectangle that I can find the area of. Well, to find the area of that rectangle, what I've done, you'll notice, this base at the bottom base did not change. So that was always what I would call the base. And the height of the parallelogram didn't change either. Even the top bit here, I've got this extra bit here, and I've taken away this bit, which was only as much as I needed to take away to make it add up to, check this out, I only took enough to add up to the bottom base, right? So even the top portion ended up the same. Now what I have is just the equation base times height. And you'll see because all we did was move pieces of this shape around, right? I didn't take anything out of here that would cause problems. If I was to, highlight this part right here, move it over here, I haven't really caused a problem by doing that, right? It's still the same area, just rearranged. You see? If it's the space that you cover, it doesn't matter whether I cut it into slices and spread those out. It's still going to cover the same amount of space, right? I can rearrange the pieces of it and still cover the same space. So for a parallelogram, the area of a parallelogram is still base times height. Now, if I get rid of all this rearranging I did, okay, and let's just look only at the original base and height. Again, not even needing to actually take anything away, right? And you get base and height. We know that we can rearrange all parallelograms this way. So that means all parallelograms you can find the area using base times height. In other words, every parallelogram is just a tilty rectangle, right? You can imagine that I've taken a rectangle and I've just tilted it over. If you have papers at home, imagine stacking up a bunch of sheets of paper and then leaning over the tower. The area that you look at straight on at the piece of papers, right, when you look straight at it standing up, that area doesn't change when you tilt over the tower. That's what this represents, okay? So the key takeaway here, we now have the equations for a rectangle and for a parallelogram and for a square, because all rectangles and squares are just parallelograms. They all use the same basic equation. Base times height equals area, right? Now, this strategy we used of seeing the rectangles hidden in objects, we're going to use that again in our next video to be able to find the area of some other basic polygons, okay? So I look forward to seeing you there. Hope you have a good day.